Class, this video is on topic B10, collisions in two dimensions. So we have in our last video talked about head-on elastic collisions, and that was when the velocities before and after those collisions were in one dimension. Now let's take a look at collisions in two dimensions, and I like to call this lesson so you want to become a pool shark. Just getting the exit ticket out of the way at the beginning of the lesson this time. Okay, but in all seriousness, for this lesson, if you want to start thinking about a situation when you've played pool or billiards, you rarely hit one ball to hit the other ball head on. So if you hit in this direction, you would hit them head on, but instead you're going to offset. So most pool shots are not head on. They're what's called angled shots or cuts, meaning that the cue ball or the white ball doesn't strike the colored ball dead on or center, dead center. We say this first picture here is thinner or more glancing than the last picture. And the thinner it is, or the more glancing it is, the greater the angle between the colored ball and the trajectory of where the cue ball would go. And one way that if you're a pool shark that you would plan your shot is by estimating the fullness of the hit. So if you angle your line of sight along the trajectory of the white ball, at the moment of the collision, you're going to ask yourself, how much overlap would there be from your perspective? And the answer tells you how full the collision is. So if there's a 1/4 overlap or a 1/2 overlap or a 3/4 overlap, that's your fullness. So if they were perfectly overlapped, that would be a fullness of 1. That would be a perfectly head-on elastic collision like we did in B9. But if the cue ball only covers 1/4 of the colored ball when you are at that line of sight, then you've got 1/4 full and you have a pretty high angle of sort of deflection of the colored ball. And there are tricks to this. So if you imagine line up your line of sight so that there's an overlap of 1, so a head-on collision, and then you angle to subtract 1/4. So every time you subtract 1/4, you add about 15 degrees. So here, when we take away 1/4 from a full overlap, you get a 15-degree angle. And then you subtract another quarter, then you get 30 degrees. And if you subtract another 1/4, you get about 45 degrees. So it's not exactly linear, but these kinds of tricks, there are many resources if you want to read up on the mathematics of pool. And so here's just a visual where you might do this automatically without thinking about the math, but he's lining up, he's got a line of sight where the cue ball would be going, and he's looking at the overlap between those balls to estimate how glancing this collision will be. So that's what we're talking about today is glancing collisions, and we're going to do calculations on them. First, we're going to recall linear momentum and the conservation of momentum, and recall elastic and inelastic collisions. And then we're going to solve a few problems involving 2D collisions. And we're going to be using vector mathematics today because if you remember, momentum is a vector. A glancing collision is a collision in which the first object, after an impact with the second object, travels at an angle to the direction it was originally traveling. So here, if ball 1 hit ball 2 head on, so if ball 2 was placed here, what would happen? That's actually a special case. So ball 1 would transfer its velocity to ball 2. Ball 2 would go off with the same velocity along one dimension as ball 1 had. So it's almost like ball 1 gives ball 2 the velocity, and then ball 1 would now be at rest. That was special case number 1, and mathematically you should remind yourself to convince yourself using the Hawk equations. But this is not a head-on collision. So based on how the diagram is set up, we've got a glancing collision. So the two pool balls will go off in different directions that are at an angle to the original trajectory of the first moving ball. So we're going to learn today that momentum is going to be conserved in the X and in the Y. So in glancing collisions, the X and the Y components of momentum must be considered separately. So recall that momentum is the product of mass and velocity, and that momentum is a vector. And that calculating the total momentum involves adding up using vector addition, adding up the momentum of each object. We always check the direction of each momentum vector because we have got our rules for vector addition. So recall that linear momentum of the system before a collision equals the linear momentum of the system after. And elastic, we have both momentum and kinetic energy conserved, but inelastic, you only have total momentum conserved. So we're going to be building these new problems where we use all these different terms and tools and use them all together. So just to recall, since momentum is a vector, we can only subtract the magnitudes if the directions are the exact same. If they are opposite, we can use a negative. But when we're talking in 2 dimensions, we have to use vector addition where we consider trigonometry or components. So note, to subtract vectors, we simply add the opposite. So it's going to be important in your diagrams that you set a positive direction and that you keep track of direction throughout these problems. The conservation of momentum equation can be expressed in terms of horizontal and vertical components. So we can write this law of conservation of momentum in the X and in the Y. And we're going to be doing both of these for these momentum problems that we're going to solve today. So again, to take a closer look at this glancing collision, momentum will be conserved in the X and conserved in the Y. So we have our our frame of reference set up, and we decide what is considered positive. We need to think of components because the balls go off on an angle. Notice that before the collision, ball 1 has no vertical velocity. And afterwards, the vertical components of velocity add up to 0. Now, this is a special case in pool or billiards where the 2 balls have the same mass. So what it really is the vertical momentum components will add up to 0. But since the masses are the same, we can also say the vertical components of velocity will be 0. And then the horizontal component sum will be the same as the original vector component in the X. So hopefully you can see that. So let's try some problems. In example 1, we have a 200 kilogram car that is traveling north with a speed of 3 meters per second. At the same time, a 100 kilogram car is traveling east with a speed of 8.6 meters per second. If the cars have a completely inelastic collision, what is their velocity just after the collision? So I would go back and reread this question with my highlighter, highlighting the givens and the keywords. So what are some keywords here that tell us that this is a problem that would be solved in this way? We've got traveling north and traveling east. Our initial velocities are 90 degrees to each other. So we know we have a 2-dimensional collision problem. We also see inelastic collision, which means that momentum is conserved, but we will not be using total kinetic energy conservation to solve this. So let's draw our diagram, which is always the first step of drawing your solution. I guess the second step after rereading your question. and label all the givens. So we have this 1,000 kilogram car with an initial speed given to east, and the 2,000 kilogram car with a velocity given to the north. And it says inelastic, so they kind of crash and become one mass, and they go off in some angled direction. Now, is it going to be 45 degrees? It's pretty easy to see if they were exactly the same mass and exactly the same speeds traveling at 90 degrees to each other, that it would be, you would guess it would be 45 degrees. This one is faster, but this one has more mass. So we really have to do the math to judge whether it's bigger or smaller than 45 degrees. So we start these problems like similar ones before with the conservation of momentum statement, but you're going to put an X in front of each of the velocity. You're going to add yet another subscript. So it's going to be M1VI1X, M2VI2X, M1VF1X, and M2VF2X. Thankfully that we have, why does this term cancel to zero? We do not have any vertical, or sorry, which one is this one? This one is M1. We don't have any vertical component of velocity for, horizontal component. We don't have any X, VI1X is zero. So that whole term cancels out. And then as well, since it's inelastic, M1 and M2 can be collected because VFX is the same. It can be factored out. So we get an equation that's VFX, that's the final velocity in the X of the whole thing stuck together, is M2VI2X over M1 plus M2, and we substitute our numbers in. Notice on my diagram, I set a positive direction for up, down, and left, right. And when I go to sub in my numbers, I have to sub in my numbers as positive or negative. So be very aware of that. So VFX, the final velocity of this crash, in the X component of that is solved. But we need to do this all over again for the vertical. So now in the vertical, we have VIY that is not zero, but VI2 is zero. There is no Y component of this eastbound car, or there's no, I guess, north or southbound component. So we're gonna write it out again, and VI2Y cancels to zero. And similarly, we isolate VFY. So we have the vertical component of that final velocity of the crash is also solved. And as we did with any vector component questions, you have to put the X and the Y together at the end. We do that using Pythagorean theorem and tan inverse to solve for the angle. So our final answer is that our car crash moves at a velocity of 3.5 meters per second at an angle east, 35 degrees north. So if we go back to those original thoughts that this is not going to be exactly 45 degrees, it's going to be more to the east. So this speed is sort of more important in pushing this car crash to the east than this is pushing it to the north. And yeah, so that's example 1. And we have another example. So in this example, it's an 8 kilogram mass colliding elastically with a 5 kilogram mass that is at rest. Initially, the 8 kilogram mass was traveling to the right and at 4.5 meters per second. After the collision, it is moving with a speed of 3.65 meters per second at an angle of 27 degrees from its original direction. And what is the final speed and direction of motion for the 5 kilogram mass? Notice we're given a lot more information here, and what it really boils down to is that this is not inelastic like our previous one, which could be simplified a little bit more with VF factoring out. So we need more information in order to solve it through momentum. Otherwise, we would need energy, conservation of energy. And let's see if we do need that. So drawing our diagram, labeling the positive direction, label the givens. You don't have to use a protractor to get this angle exactly, but do estimate it. So it's 27 degrees, don't draw it bigger than 45. 8 kilogram mass, 4.5 meters per second to the right. And then we're given information about the final velocity of the red, what I'm using to color code it as the red. That's the 8 kilogram ball. The blue 5 kilogram ball was off on in this direction. It's originally at rest, and we are looking for the final velocity, which will involve knowing the horizontal component of it and the vertical component of it, and then putting them together. So let's start from conservation of momentum in the x, and we can solve, we can simplify. VI2x is 0 because it's at rest. And then we simplify to get a certain equation. We substitute in our numbers. Pay attention as to whether these are going to go in as positive or negative based on your the way that you assigned the positive direction to be. And we get an x component. And for the y component, it's even a little bit easier because we set this to be y, which is exactly 90 degrees to how this is moving. The vertical component of this velocity is 0, and this has an overall velocity of 0. So those first two terms cancel out to 0, and if we add up the vector quantity momentum of the two objects at the end, they add to 0. So visually, what does that mean? This vertical component here equals the vertical component here. That is of momentum. Momentum up plus momentum down equals 0. It's not, in this case, velocity up and velocity down equals 0 because the masses are not the same. If the masses were the same, then it would be simply the velocity up plus the velocity down equals 0. So we calculate a vertical velocity of negative 2.65 meters per second. Why is it negative? It makes sense because we said positive was up. We subbed in 3.65. Wait, is that the number? Yeah, 3.65. We subbed that in as a positive, saying this direction is positive, therefore this is negative. So we get a negative component of the y. We put those together again. We've got 1.99, 2.65. Pythagorean theorem gives us the length of that total vector, final velocity, and then the angle. So the final speed is 3.3 meters per second, and the direction is 53 degrees away from the line along which the 8 kilogram ball was hit. So what was really important in these problems was that we had a diagram, we set a positive direction, and we were very clear with our conservation of momentum statements. With all of those subscripts, it was very clear and readable, legible, so that we could double check our work at the end. And in B10, what's new is that we have to do conservation of momentum in the X and in the Y. So now it's time for you to do some practice questions. So make sure you're checking your textbook solutions at the end, submitting your exit ticket, practice these questions, write them down, practice with practice for full communication marks. And I'm gonna link a bunch of interactives that are really useful below this video, so you can visualize some of these two-dimensional collisions and play with some of the settings, possibly look at some of the special cases as well. So have a great day and good luck on the problems.